Let's go with this one. Okay, any questions? No questions on torque? The answers for 4, 5, and 6 I put on here, so because there's no answers, so that they're boxed right there. Let me change colors again.
Could you explain number 6? I got it. I got that question wrong, so
The mountain climber?
Yeah.
Yeah. Okay, so the mountain climber is drawn as a box, which doesn't really help, but when the person's hanging from the rope, they're like, you have to pretend that they're like hanging from the rope like this, where their feet are pushing against and their hands are on the rope like that. And so they're pushing against the cliff that way. And so because of normal force is like a reactionary force of a surface against something pushing against it. So the cliff will push back with normal force going that way. And so the three forces you have are the tension in the rope holding the person up, the gravity of the person going down, and the normal force pushing the person away from the cliff. And so those are your three forces acting on it. And so if you add those together, you get like tension plus normal force plus gravity equals 0. And then this is 12 degrees right here. So that would be formed right here, 12 degrees, which means that this is also 12 degrees. And this is a 90-degree angle because they're pushing horizontally on the cliff, which means the cliff is pushing back horizontally. And so Fn and Fg are perpendicular to each other. And yeah, so then you have your Fg, which is 735. So you can solve for your tension. It's just a right triangle. Does that make sense?
Yeah, thank you.
Yeah. It's kind of confusing because it says that the climber is pushing, but you have to analyze the forces that are acting on the climber. And so even though it's the climber that's pushing against the wall, you're analyzing it from the point of the wall pushing back on the climber. Any other questions, specifically torque?
Then I have a question for number 5. Sorry.
Yeah.
I only see friction and Fg, but I don't see Fn. What happens to Fn?
So Fn would be this one right here.
Mm-hmm.
But that's not acting on the point where point in question. The point in question is right here. And so I only care about this tension, this gravity, and this tension. But because this tension, like, you're trying to find out what the maximum weight is, because if you add a lot of weight, then this block will eventually pull that way. So you're finding the point at which this force and this force are balanced. So the friction is the tension.
Oh, okay. Yeah, thank
So yeah,
you.
because there's another gravity here as well, acting on the 15, but it doesn't. It's not doing anything.
Matter. Oh, okay. Thank you.
Loving these questions. Keep them coming. Nothing about torque? Not even number 7?
No, I was gonna ask that. Can you do number 7?
Yeah. Okay. Give me a sec. Number 7. Okay, people are asking for number 7 now. Okay. The reason number 7 is difficult because it doesn't tell you where the pivot should be, so it's a little bit more difficult. So uniform 400 Newton diving board. So the diving board itself has mass. Is supported at 2 points as shown in the diagram. If the diver stands at the end of the board, what are the forces acting on each support? So What I want to do first is figure out where all my forces are, but I'm not quite sure what the forces are doing at both supports. So I'm just going to assign a pivot at this point right here and then say, okay, so the diver is going to stand on the board, which is going to go down like that. That's the diver's FG. And so that's going to cause a clockwise torque, okay, when I assign the pivot right there, because that'll bring the board down. And then halfway down the board, there's also the FG of the board, which is also going to cause a clockwise torque. And so going based off of those two, the force here has to be upwards. Okay, the normal force of the support on the diving board has to be upwards because we need a counterclockwise torque. Okay, and I'm going to assign it that way. So let's just start the problem like this with the pivot there, and then I'll show you what it looks like if we make the pivot in the middle. So if we do that, so we have two clockwise torques, one counterclockwise torque, and they have to be balanced. So torque clockwise plus torque clockwise has to equal torque counterclockwise. Okay, and stop me if you have any questions if you're not quite understanding why I'm choosing a pivot or not, or what I'm doing. Okay, so then my 2 clockwise equals my 1 counterclockwise. And so I'll just start going like right to left, I guess. So we have the FG of the diver, 75 kilograms. So this is going to be 735, 75 times 9.8. I think that's 735. Let me double check that. Yeah, 735. And the torque that it causes is going to be the force times the distance. So this is going to be 735 newtons times 2 meters, because it's all the way 2 meters away from the pivot, plus the 400 Newton diving board, 400 Newton diving board times 1. Okay, it says it's a uniform board, which means that the center of mass is in the middle, and that's where the force of gravity is acting, equals Fn times 0.5, 0.5 away from the pivot. And then all we got to do is figure that out. So 735 times 2 is 1470 plus 400, so 1870 equals 0.5 times Fn. So times that by 2 again. So you get Fn is, why am I getting a different answer? Left support, right support. Why am I getting a different answer? Read the question, end of the board. Let me double check this. Times 2 plus 400, 1870 divided by 0.5. Oh, I totally did that wrong. Okay, I typed it in my calculator wrong. There you go, 3,740 newtons. And that's going upwards. Okay, we know that it's going upwards. So that's why it says up in the, I'll just make this positive, I guess. And then to find the force on the other support, there's kind of two ways you can do it. You could either go with torques again, or with your sum of the forces has to equal 0. And that's the easier way to do it, really. So because the sum of your forces has to equal 0, then whatever force this is, we're just going to call it F, plus this Fn that we just found, 3740, and then minus 400 minus 735 equals 0. Okay, because all the forces have to equal 0. The two FGs are going down, which is why they're both negative. So then we'll go 3740 minus 400 minus 735. And then so F would equal negative 2,605 newtons. And this negative means that it's going down. Now that might seem counterintuitive. Okay, a lot of my students see this question, they're like, well, both of those supports should be going up because the normal force should be going up. To explain this, I'm going to erase. Are there any questions about what I just did before I erase it? No, we're okay. Okay, I'm only going to erase these and make my pivot right here. Okay, so if I make my pivot right here, this FG is still going to cause a clockwise torque. This FG is still going to cause a clockwise torque. And then I need this one to cause a counterclockwise torque. So if it was going upwards, that would cause a clockwise torque. Well, then I would have 3 clockwise torques, and that wouldn't work. Okay, so that means that there has to be a force pulling the board back down. Okay, so that's how you know that it has to be going down. Hopefully that makes sense. Did anyone choose this as your pivot point? Okay, if you did, it would be the exact same setup. Torque clockwise plus torque clockwise equals torque counterclockwise. It would just be 0.5 times 400 and then 1.5 times 735 and then 0.5 times your Fn or whatever that force is called.
So does it not matter which one you set as a pivot point?
No, as long as it's one of your 2 unknown forces. Like I can't make it this force, this like where the diver is, because I know what that force is, so I don't want to get rid of it.
Mm-hmm.
Yeah, it doesn't matter which support you make your pivot.
Mm-hmm. Okay. Mm-hmm.
Okay. You guys ready? This next lesson sucks. It's pretty difficult. Okay, so forces cause torque, but only forces that are away from the pivot cause torque. And new rule, they have to be perpendicular to the lever arm in order to cause torque. Okay, imagine you were trying to push on a door that way. Okay, it's not going to rotate. You're just going to push it towards the hinges. It's not going to rotate at all. So if we have forces that are at an angle to a lever arm, whatever that angle might be, let's call it theta, it's only the perpendicular component of that force that's going to cause torque. And there's 2 ways to kind of set this up. You can either draw your components like this, where you're completing the triangle with theta. I'm not a big fan of doing that because then it looks like the force that's causing the torque isn't actually acting where the force is acting, because it's acting right here, not right here. Okay. So I like to break it. So if that's my force and that's theta, I like to break it into forces that look like that, where this angle is theta right here. Okay, and this would be the force. That hypotenuse is the force. And so which one causes the torque is this arrow right here. So we'll call this F perpendicular, and this is called F parallel. So if you look at like F perpendicular is actually opposite of theta in both triangles. So it's going to be sine anyways. So sine theta equals opposite. So F perpendicular over F. And so what we get is the force that causes the torque is F sine theta. Now, I don't really want to say it's always going to be sine, because sometimes they'll give you this angle right here, and then it would be cos theta. So as long as you understand that it's going to be a component of the force, either sine or cos, then it doesn't matter what it is. But in general, the formula, rather than saying torque is equal to force times distance, it's actually force that's perpendicular times distance. And this is either F sine theta or F cos theta, depending on which theta it gives you. Okay, does that make sense? Okay, that part's pretty self-explanatory. It's the actual problems that are a little bit more difficult. So let's jump into those. All right, so here's, and I'm going to draw another example as well. So a 45 newtons sine hangs from a hinged uniform beam. So this is the hinge right here. That's 2 meters long and weighs 29 newtons. So the beam itself, or sorry, the beam itself has a weight and the sine has a weight. Supported by a rope that makes an angle of 33 degrees with the beam. So 33 degrees with the beam. What is the tension in the rope? So what we want to do is we want to start drawing in our forces, just like a free body diagram type of thing. So 45 newtons sine, so this right here is 45 newtons. Okay. Uniform beam that's 2 meters long and 29 newtons. So halfway down the beam, there's another force that's 29 newtons. And so, and these are both perpendicular. So this is torque clockwise, this is torque clockwise. And then the force that causes the counterclockwise torque is the tension in the rope. Okay, and specifically this tension right here, the perpendicular tension. And so this is your counterclockwise torque. So then I'll have torque clockwise plus torque clockwise equals torque counterclockwise. And then we can just start putting things in. So the first one right here, the weight of the beam, is going to be 29 newtons times its distance, which is halfway because it's a uniform beam. So the beam is 2 meters, so this is going to be 1 meter, plus the weight of the sine, 45, and it's 3/4 of the length. Okay, so 0.75 times 2, 3/4 is 1.5 meters. And so it's acting 1.5 meters away from the pivot. And then in this case, it's technically T perpendicular. So this is T perpendicular times D. Okay. So if this is theta right here. And so we're dealing with that theta being sine. So T sine theta is T perpendicular. And so I'm going to write T sine 33. So that's the force that's perpendicular to the beam times its distance, which is 2, because it's acting at the end of the beam. Okay, does that make sense? I hope it does. So then 29 plus 45 times 1.5, 67.5 equals, I'm just going to keep this as T sine 33 times 2. Plus 29, so that's 96.5 equals, I'll move that 2 there. And then I can take the 96.5, divide it by 2, and then divide it by sine 33. And that gives me a tension of 88.6 newtons. Okay, and that's the tension in the rope. The next, any questions about that? Okay, same thing we've been doing all along, so it's not that difficult. The next thing I would ask on a question like this is, what is the force at the pivot? Okay, and there's probably an X force and a Y force acting at the pivot. And so let's answer force at hinge. Okay. The tension is pulling the beam towards the wall. right? Because this is the tension parallel is pulling the beam towards the wall, which means that the wall has to be pushing back. And so if you look at the forces in the x direction, we have Fx, which is going to the right. Well, I'm just going to add them all together. So the Fx plus Tx equals 0. Okay, there's only two forces in the x direction, and they should equal 0. So if I do it that way, Fx, whatever it is, plus Tx, so this, I made it T parallel, but it's Tx. T perpendicular was T sine theta, which means Tx or T parallel is going to be T cos theta. So this is going to be 88.6 cos 33 equals 0. And then you'll see, oh, I also have to make this negative, okay, because it's going to the left. So it has to be negative. So if we do that, cos 33, then we get Fx equals positive 78.9 newtons. Okay, and I'm getting confused a little bit with the directions, but it makes sense. If the tension's pulling the beam towards the wall, then the wall is going to push against the beam away from the wall. Okay, now for the y's, all you have to do is start figuring out what all the forces are. So we have T perpendicular, which is going up. We have Fg of the sine going down, Fg of the beam going down, plus whatever that Fy is has to equal 0. Okay, so this is going to be 88.6 sine 33 minus 45 minus 29 plus Fy equals 0. So 88.6 sine 33 is 48.255 blah 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 minus 45 minus 29 equals negative 25.7 newtons plus Fy equals 0. So then you solve it, Fy equals positive 25.7 newtons, which means that that force is going up at that point. And yeah, and you can double check that by making this your pivot, right? If you make the end of the beam the pivot, then this is going to be counterclockwise, counterclockwise, and then this has to be clockwise. So that's how you know it's going up. You can just double check that it's going up that way. Okay, any questions about that? Let's see, could you explain how you got T, the tension? The 88.6? Yes. Okay, so I kind of need to start over in order to do that. So the pivot is, let me redraw this. So if you think about the forces that are acting on the beam, on the whole system, you have tension going this way. You have Fg of the beam going down. You have Fg of the sine going down. Okay, so there's three forces acting on the, and then whatever's at the pivot, but it doesn't matter because it's not going to cause torque. So the tension's going up and left, so it's going up and left. In terms of torque, the perpendicular torque is, or perpendicular component of tension is the only thing that causes torque. So this is going to be a torque clockwise, torque clockwise, torque counterclockwise. And then so they have to balance. So this torque clockwise plus this torque clockwise has to equal this torque counterclockwise, which is this equation right there. And then all you're doing is putting in each individual force times distance. So 29 times 1, because it's 1 meter away, 45 times 1.5, because it's 1.5 meter away. And then in terms of torque, it's the T perpendicular times the distance. And so T perpendicular as a function of T perpendicular is T sine theta. Okay, so that's where I'm getting the T from. I'm solving for the hypotenuse of the tension, okay, by using the T perpendicular causing torque. So T perpendicular times the distance, T perpendicular is T sine theta, distance is 2, and then you're just solving for time, or for tension. Okay, hopefully that answers your question. So T perpendicular doesn't equal TCC. T perpendicular is a force that causes counterclockwise torque. So that your tension and like this is tension, it's not torque. Torque is the little tau, it's the curved T. Okay, just checking. It's T perpendicular times D is torque counterclockwise. That's exactly right. It's the perpendicular tension that causes the torque. Oops. Okay, perfect. Okay, the next example I'm going to do, I'm not actually going to solve anything. I'm just going to show you what it looks like. Because it's a whole new deal that you will eventually need to solve. So let's assume that we have, oh boy, let me actually try this really good. Come on. Let's assume we have something like this. And then we have a beam that is at an angle. Okay, so let's call this, let's just call it 60 degrees. Okay. And let's say we have a sine hanging from the beam as well. Okay, now I'm just going to draw. Okay, the sine hanging from the beam, and let's say we have another rope, and this would be, let's say, 50 degrees. Okay. Now, assuming that the beam itself has mass, if we look at all the forces acting on this beam, we have gravity of the beam itself, gravity of the sine, Fg, and then we have tension going that way. Okay. None of these forces cause torque on their own. Okay, none of them are responsible for individual torques. It's the perpendicular component of the forces that cause torque. And so what you need to do is you kind of need to imagine this as a triangle where this is your FG perpendicular and this is your FG parallel. Okay, just like our inclined plane that we figured out yesterday. Okay, where this is your FG perpendicular and this is your FG parallel. Okay, now when you do it that way, that's how you have to do it. You have to find the perpendicular component. If this angle right here is 60, then this angle right here has to be 60 as well. 60. Okay. And then right here, the tension up here, again, you need to break it into parallel and perpendicular. Okay. And again, this is 50 degrees. So if I were to solve this problem, this is my pivot point right here. And let's say this is, well, I'll just come up with random distances in a sec. So in terms of torque, change colors again. This is going to cause a clockwise torque. This is going to cause a clockwise torque. Actually, let me draw this where it's actually going to go. This is going to cause a clockwise torque. This is going to cause a clockwise torque. And this is going to cause a counterclockwise torque. Okay. And so it's the same setup. It's still TC plus TC equals TCC. But in this case, it's going to be, so let's call this 1 and let's call that 2. So TC1 is going to be this component times D. So it's going to be FG perpendicular times D plus FG perpendicular times D equals T perpendicular times D. Okay, so it's not the force, it's the component of the force. And then all you have to do is figure out what this is in relation to FG. Because you're going to have the mass or the weight, you're not going to have the perpendicular. Okay, this is your given value, which means you need FG perpendicular as a function of your given value. And so if I use this 60 degrees, I know that it's going to be sine 60, because notice how this is the right angle right here between the perpendicular and the parallel. And so this is your hypotenuse, the FG. Sine 60 is going to be FG perpendicular, opposite, over FG, your hypotenuse. And so FG perpendicular will be FG sine 60. Okay, and so then plugging that into our torque formula, FG sine 60 times, it's a uniform beam, so 0.5 times L, whatever L is, halfway, plus FG of the sine now, it's different FGs, times sine 60, times, let's just call it 3/4 again. Whoops. I don't know why I used L, D, equals, and then this one's a different angle. Okay, it's 50 degrees, not 60 degrees. And so this will be T sine 50 times D. And it's acting at the end, so it's D. Okay, it probably seems like a lot. Hopefully it makes sense in terms of breaking individual forces into components and finding which components actually cause torque. Any questions about that one?
Can you show me situation that uses cosine, like just for example?
Yeah, well, I mean, I could change this to 40 degrees and call it cos 40.
Oh.
Right, so it just depends on what angle I choose.
Yeah.
I just don't want you guys to, like, every time in the past where I've said, okay, let's make it F, like I would say torque equals F sine theta times D, everyone would memorize this formula and not apply the angle properly. Okay, because it depends on what angle you're using. So I'd rather you just look at the triangle and decide what angle you want to use from the triangle. So I'm not going to set it as either sine or cos. It could be, it depends on what angle you were using.
Okay, thanks.
Yeah. Yeah. And you'll come across problems like this, so it's not. Yeah. William, I don't understand what you mean by is the angle 60 used. It's showing right here, 60, 60.
I just want to make like clear, like the 60 angle is from the left triangle that was already in from
This 60 right here?
Yeah. Yeah.
So that's how I'm getting this 60 right here. It's the relationship between the vertical line here and the angle of the beam, 60 degrees. It's the same relationship as the vertical line of FG and the FG parallel.
Oh, it's the theory. So it's always like that.
It's the relationship between the two diagrams where this angle is the same as this angle.
Oh, yeah.
Yeah. Yeah, so like this straight line right here is parallel to this straight line right here. And this FG parallel is parallel to this line right here. So the angle formed between both lines is going to be constant between every triangle, except for this triangle because it's a different angle.
Okay.
Okay. And then for this type of question, I probably wouldn't ask for the force at the hinge, but if I did, it's really hard to break into XY because we're breaking every triangle into parallel and perpendicular. And so if you were to find the force at the hinge, you would do it as force parallel and force perpendicular rather than Fx and Fy. Okay.
All right.
So yeah, makes it easier. Okay, so the worksheet, you guys can continue on the next angled stuff. So there you go. And like, yeah, so this is the first example where you have to use the FG as being a component. And keep in mind that this is the angle. That's the torque or the tension that causes the torque. So you have to analyze it from that point of view. And then, yeah, another one right here. So you will run into them. What I'm going to do is in the files tab of the team, I'm going to upload the review package for this unit because we're done equilibrium now. And so you'll have a bit of time to work on that. Monday, we're gonna Monday won't be the test for this unit. It'll be on Tuesday. That gives you an extra day. But Monday I want to do a short lesson on energy because we need to start talking about energy and momentum. So that's the plan for now. And let's do that at 8:30 again on Monday. So we'll do a short energy work lesson, and then the test will be posted on Tuesday for equilibrium. But I'll post the review right now so that you'll have the opportunity to do it over the weekend if you want. And then again, if you have questions over the weekend, just message me or whatever. I have family in town right now, so I might not be too available, but I might be. So just message me with questions.
So
any other questions?
So the class on Monday starts at 8:30 in the morning?
Yeah, we'll do a lesson at 8:30.
Okay.
Any other questions?
Will the test be the same as the quiz, same sort of format?
Yes. Yeah, I have to use OneNote because it's just unfortunate, but guests out of district students don't have access to Microsoft Forms, or at least they can't upload pictures to Microsoft Forms, and so that kind of puts a damper on things.
So yeah, we have the whole day to work on it, just like the quiz?
Pardon?
So we have the whole day to work on it, just like the quiz? Okay.
Yeah.
Okay.
But I'm out of district, but I was able to post pictures.
On OneNote, yes. But I typically use Microsoft Forms for assessments, but you're not able to upload pictures to Microsoft Forms. So,
okay.
Yeah. That's okay. We can use OneNote. In the future, for the next test, I realize now that we need, when you upload your answers to OneNote, it has to be titled the exact same thing. So you can't just call it whatever you want. So I'll tell you that when I upload the test, but it has to be called equilibrium test answers. It can't be called untitled page or whatever you want. So I'll remind you again when we actually get to the test. But because right now I'm looking, I'm trying to mark all these tests, but I'm going through it and trying to find them all, and I'm going by, it's just confusing when they're all titled something different. So we'll work the kinks out. Okay, any last questions? Okay, if you have questions, just message me. So that's it. Have a great weekend. And I will see you guys Monday.
Thank you. You too.
Thank you.